Okay, so last time I said we did a lot of limits with graphing calculator. So we're going to do shortcuts on how to not always use the graphing calculator. We're going to use it a little bit for these. So the first thing on 12.2 that we're going to look at are these rules, these basic rules for evaluating limits. So the first rule is if p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is equal to p of c. And you don't have to write this down, you could always look it up. But basically it just says you can direct substitute, right? We can substitute c into this polynomial if it's like x squared plus 3x plus 2. And I want to find as x approaches 2, I could just substitute that value in, right? Kind of like number 1 right here. If I have this polynomial function, all I have to do is substitute that -1 in there, and I'm going to get a number, and that's going to be my limit, as long as this is some continuous function. And this is just quadratic, so it's continuous, and it's not going to do anything crazy. Okay. The second rule here says if r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c does not equal 0, then the limit as x approaches c of r of x, or r of c, we're going to plug this c into there, is the same thing as p of c over q of c, because r is p over q. So p over q is just like two polynomial functions, and again, all you have to do is plug that number into there, and as long as you don't get 0 over 0, that's going to be your limit. So it's just direct substitution, okay? So we'll look at example 1 here. We'll do example 1 together and write it down. And it says that we're going to have the limit as x approaches -1. Be careful of those negatives. They're really small and kind of hard to see. Of x squared plus x minus 6. So since this is just a polynomial, let's plug it in. Right? Let's plug in -1 into the function and see what we get. So I'm going to get -1 squared minus -1 minus 6. -1 squared is 1, and then we're going to plus 1 minus 6. I messed up on the what? -1. Oh, this is a plus. Sorry, that is a plus right there, so that makes that a -1. So 1 minus 1 minus 6 equals -6. Okay, so that's going to be our limit, because we actually got a number. If I were to graph this, x squared plus x plus 6, what would it look like? Would it be a line? It would be a parabola, right? And at -1, we care what's happening at -1, and it's going to, I don't know, do something like this, and I know it's at -1, -6, because we got -6 when we plugged in -1. And so the limit is going to be -6, because from the left it's approaching -6, from the right it's approaching -6. So that's the limit. Okay. That's all that's saying. Part B says, okay, let's take this limit as x approaches -1. We're going to have the same function for our numerator, x squared plus x minus 6, but this time we're going to divide it by a denominator, x plus 3. So we're going to have some p of x divided by q of x. Well, let's plug in -1 and see what happens to this. Well, if I plug in -1 to the top, we already did that. That's going to be -6, right? Because we did that up here. And if I plug in -1 to the bottom, -1 plus 3, I'm going to get -6 over 2. So -6 divided by 2 is -3. Since it's a number that doesn't equal 0 over 0, that's good. That's the limit. If I were to graph this on my calculator, I could see where the limit is approaching from the left and the right. Okay, so it's easy. When you plug in a number and you get a number, awesome. That's all you have to do. Okay, we talked about that a little bit yesterday. Now let's do something a little differently called the dividing out technique. Okay, and so I'm going to use this limit, but I'm going to change this number to x as x approaches -3. So if I take the limit as x approaches -3 of that same function, x squared plus x minus 6 over x plus 3, what's going to happen when I plug in -3 here? Yeah, that's our problem spot, right? Negative 3 plus 3. Let's go ahead and plug it into the top two. Negative 3 squared, minus 3, minus 6. And yeah, that's going to give you a 0 in the denominator, right? Negative 3 squared is 9, and then minus 9 for these two are going to add up to negative 9. So you're going to get 0 over 0. Okay, what do we learn that is, what is that equal to? That's undefined, right? We learned that yesterday, last class. Undefined. Okay, we also have a special name for this. This is called the indeterminate form. Indeterminate form. That's it's on the top of the next page, page 818 in your book. When you get 0 over 0, that's actually a good thing. It means that sometimes this can be changed, and it can be this has a common factor with this, so we can factor it out, right? So can we factor the top? Yeah, sure we can. So I'm going to put, you have to write as the limit approaches x, as the limit of x approaches negative 3 again. Let's factor x squared plus x minus 6. So my x squared is going to be x times x. My 6 is differing by a factor of 1, so that'll be 2 and 3. Because 2 times 3 equals 6. 2 minus 3 is 1. I want a positive 1, so positive 3, negative 2. That's how we're going to factor that. The bottom x plus 3, that doesn't factor. But look what happens after we factor, right? We did this a lot in Algebra 2. What happens? Yeah, we can divide these out, right? Those go away, and we're just going to get x minus 2. Well, since we divided out the x plus 3, this is no longer going to go to 0. We're not going to get 0 over 0 anymore. We're going to get something else. We're actually going to get an answer, right? We're going to get negative 3 minus 2. So you just plug that into there. All right, negative 3 minus 2 is negative 5. Oh, so this does have a limit. If you factor it out and get one of the factors to cancel, it will no longer be in the indeterminate form, and you'll actually get an answer. Okay. Now, if we were to put this in our calculator, we would get something like this, right? So if we were to put x squared plus x minus 6 divided by x plus 3 into our calculator, and we did really small values and looked at what's happening around negative 3, you get negative 5.001, negative 5.0001 over here, negative 5.01. You can see it's approaching negative 5. And the right side, negative 4.9999, that's approaching negative 5 as well. So this supports our answer, you know, because this is going to say error in our calculator, right? Because when you plug in negative 3 to the original function, you get an error. So, but around it, it's going to be approaching negative 5. Okay, so yeah, that's a shortcut, dividing out. So let's go on to the next example on page 818, example 3 here. Got a piece of paper. And this one says find the following limits. The limit as x approaches 1 of x minus 1 all over x cubed minus x squared plus x minus 1. First thing we should always do is plug in the number to see what we get. See if direct substitution works, right? So I'm going to plug in 1 into here. 1 minus 1 over 1 cubed minus 1 squared plus 1 minus 1. Yeah, it looks like we're gonna get our same old 0 over 0, right? We get 1 minus 1 here, 1 minus 1 here, so that's 0. Indeterminate. So that means we can factor this, okay? Can we factor the top? No. How do we factor the bottom then? Because this one's different from the last one. Yeah, parentheses, right? Factoring by grouping. You group the first two together, you group the last two together, because this has 4 terms, not 3 terms. And that's how you factor 4 terms. It's called factoring by grouping. So what we do is, let me rewrite the limit as x approaches 1 of Can't do anything to the top. So we take out what x cubed and x squared have in common. The highest common factor of x cubed and x squared is x squared, right? They both have an x squared in there. So then we multiply by what's left. X squared times what equals x cubed? X. And then x squared times what equals x squared? 1, right? We did that a long time ago at the beginning of the year. This guy has nothing to factor out. Well, so if you have nothing to factor out, what's a factor of everything? 1. So let's put plus 1 times x minus 1. That 1 is important. Okay. Now, since when you do factoring by grouping, you're always going to get like these two being the same. Since they're the same, we're going to pull that out as a factor, okay? That's going to be an x minus 1. Those two, we're factoring them out. And then what's going to go in the other parentheses is the other stuff that we haven't factored out, this x squared and this 1 right here. So x squared plus 1 is how you factor this, okay? All over the x minus 1. Okay, look what we have on top and bottom here. Those x minus 1s are going to go away. What does that leave you with when they go away? Right, 1 over x squared plus 1. Remember, when things cancel out, please put a 1 there so you don't think that there's nothing there. There's a 1. This over this is 1. Okay, and I should have wrote the limit as x approaches 1 here. I should put the limit as x approaches 1. Forget that right there. Of 1 over x squared plus 1. Now, since we canceled out one of the factors, we can plug in our 1 into the function. We get 1 over 1 squared plus 1, which is 1 over 2. So, the limit is 1/2. Okay? We didn't get that when we first plugged it in. We got 0 over 0, but once you factor something out, you can get an answer. So let's put this in our graphing calculator just to check, right? Let's put the original function in our graphing calculator. So I'm going to put y equals. You have to put parentheses around the top, and you have to put parentheses around this whole thing, just here and here, okay, if you're going to divide two big polynomials. So parentheses, x minus 1 is the first, x minus 1 end parentheses, minus 1 end parentheses, divided by x, parentheses again, I almost forgot. I'm going to put parentheses around the bottom. So x to the third minus x squared plus x minus 1 plus x minus 1, enter, and hopefully yours looks something like that. Or that's how you properly enter it. Parentheses around the top, parentheses around the bottom. Hopefully my window is correct. Maybe it's wrong. Let's see. Let's graph it and see. Oh, so I get like this Gaussian curve, right? Let me zoom in. It looks like I don't need any negatives. So let me go window and get rid of my negatives, make that a 0, and then graph it. Maybe that'll be a little nicer. So it looks like it went up to 1 right at 0, but we're not looking at 0. We're actually looking at 1. So I'm going to press my trace button, and it goes to 0, 1, and I want to get to 1, so I'm going to make this get closer and closer to 1. When I get closer and closer to 1, it approaches 0.5, right? And that's our answer, 0.5. And when I go over 1, it's slightly lower than 0.5. If I go to my table, let's see where my table is at. There's 1 is down here. So at 1 we get an error, but you can see it gets closer and closer to 0.5. That's close to 0.5, that's close to 0.5. So the answer is 0.5. Okay? So, you know, if you need to, sometimes we're going to want to make just a little graph like that and show at 1, it's, we actually need to put an open circle there. So at 1, it's 1/2. But there actually doesn't exist. For this function, there's no value that exists at 1. You get an error. But around it, it's going to approach 1/2. So we say the limit is 1/2. Okay. Okay. That's example 3. Example 4, the rationalizing technique for example 4. Okay, let's put the rationalizing. When do we use that term, rationalizing the denominator? That's right. So we've done this before, except this time we're not going to rationalize the denominator. We're going to rationalize something else. The limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. Okay. Let's plug in 0, see what we get. When I plug in 0, I get 0 plus 1, square root of that, minus 1 all over 0. Which gives me square root of 1 minus 1. Oh, that's 0 over 0. Surprise, surprise, we get 0. This tells 0 over 0. This tells me there's at 0, there's a gap. There's some kind of hole in the function at 0, right? But so we want to look at what's going around 0, what's going on around 0, to the left of 0 and to the right of 0. So to do that, if we can get something to cancel, this is going to work. And we are going to get something to cancel. So let me rewrite this. Limit as x approaches 0 of the square root of x plus 1 minus 1 over x. Let's get this to cancel by multiplying by the conjugate. Okay, what would the conjugate of square root of x plus 1 minus 1 be? It's going to be the square root of x plus 1 plus 1. So remember when we multiplied, when we did real numbers and complex numbers, when we did like a plus bi, and sometimes we wanted to multiply it by a minus bi? That is called the conjugate. Conjugate. It's like the opposite. Okay, but you only make this last term opposite. So this minus 1 becomes a plus 1. That is the conjugate. And whatever I do to the top, I have to do to the bottom. So we're also going to multiply it by the square root of x plus 1 plus 1. Okay. Now watch what happens when we do this. When we multiply this times this, right? Square root of x plus 1 times square root of x plus 1, what is that going to give you? X plus 1. Wow, we got rid of the square roots. That's kind of nice. And then we also multiply the last two. Negative 1 times positive 1 is negative 1. Why didn't I do the other two multiplications? Why didn't I do this one and that one as well? They're going to cancel, right? This negative square root of x plus 1 is going to cancel with the positive square root of x plus 1. So we don't need to do those. That's why you multiply by the conjugate, because those are always going to cancel if you make this one minus and this one plus. So that's a nice little trick. And then this thing we have to multiply, but we can't really multiply, so I'm just going to write it x times the square root of x plus 1 plus 1, like that. Okay, and the limit as x approaches 0. Always write that till you get into the end. You always have to write this until you actually plug in the number, then you don't write it anymore. You don't write the limit anymore, okay? So now we're actually going to plug it in. Oh, and this minus 1 plus 1, this goes away, right? That's just 0. So really we just have x over x. Oh, x over x. What can I do with that? Those can cancel, which gives me, so let me put the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Okay, and that's always going to happen too when you rationalize the numerator. This time we're rationalizing the numerator, not the denominator. You're going to get this common factor that's going to cancel, and that's why you're able to now plug in 0 into the function. Okay, so now we plug in 0. We're going to get 1 over the square root of basically 1 plus 1. So what's our answer? 1/2, right? 1/2, just like the last time. So if we put this in our calculator, okay, let's go ahead and put this in our graphing calculator. Put y equals, and the original function, so we're going to have to put square roots around the whole top again. So we're going to put square root around this, a parentheses around the square root. So you have to put a parentheses, or you don't need to do it for the bottom because it's just one thing. So parentheses, square root of x plus 1 end your parentheses, and minus 1, end your parentheses again for the numerator, divided by x. So it should look like that in your calculator. And let's graph it. Let's press graph and see what we get. Oh, nothing. Oh, there it went. So I got a upside down sleeping parabola pretty much, right? Because we have a square root function in there. But where are we looking at? We're looking at 0. And I know at 0 there should be a hole. So your graphing calculator is never going to show that hole, but right at where it crosses the y-axis, there's a hole there. And so at -1, 1 is where the graph starts. So if I were to graph this function, I would say here's -1, 1. I'm going to start the graph here. And it's going to go through, I know it's going to go through a half, but there's going to be a hole there, so I'm going to go like that. And it looks like eventually it does cross the x-axis. We just can't see it in our calculator. Maybe not. Maybe it's approaching the x-axis. But yeah, there's definitely a hole at 0, 1/2. Okay. But there's still a limit. Even though there's a hole in the graph, the limit is at 1/2 because it's approaching 1/2 there. Okay. That's how the limit works. Okay. Okay, and the next part says using technology. So let's use technology. Sometimes we have to use technology and we can't just use our awesome algebra skills to make things cancel out. So example 5 is approximate the limit of the limit as x approaches 0 of 1 plus x to the 1 over x power. Okay, so let's plug in 0 into here just to see what we get. We get 1 plus 0 to the 1 over 0, which is basically 1 to the 1 over 0 power, which 1 over 0 is undefined, so we can't do 1 to the undefined power, right? So, yeah, try it in your calculator, see what you get. Can I simplify this? Can I factor it and make something cancel out? No, right? You can't factor this. So we can't use that little trick anymore. So what do? We have to use our technology. We have to use our graph. Okay, so let me switch. These buttons are a little sticky, so let me switch here. So let's plug it into our graphing calculator. So we have parentheses 1 plus x parentheses to the, and then you have to put parentheses around this, right, when you enter this in your calculator. 1 divided by x. So, you know, half of this lesson is entering things correctly into your graphing calculator. And that takes practice. So 1 plus x to the 1 over x. Let's see if we get a graph. I forget what graph won't we get. Okay, so we do get a graph. At 0, though, I know there's a hole at 0, so where it crosses the y-axis, there should be a hole. It kind of looks like an exponential decay problem, right? So, and it looks like, ooh, 1, 2, more than 2.5, it looks like, right, that it passes up there. So we're interested, what is that point that it passes at, even though there's a hole there? So how do we check that? Second table, right? Second graph to get your table. Oh, and I put my table at really small increments. So do second table set and change it to 0.001 because you want it to go really close to that. Okay, and don't worry about that. As long as you put 0 here, I think that just automatically came up. Now when I go to my table, so I get an error at 0, but look at the numbers above 0 and below 0. 2.71. What number is that? That's a special number. It's E. Yes, that's E. So this is approaching E. Okay, and we need to recognize that. We can't see it in our problem, but because our table looked like this, because we had let me write negative 0.002, 2.71. negative 0.001, 2.71. 0, error, right? There's a hole there. 0.001, 2.71. 0.002, 2.71. Well, since they were all 2.71, there's little variations after the 1, but they're all close to 2.71. So our limit as x approaches 0 is approximately, of our function f of x, is approximately e. Okay, because we looked at the values around it and we had to put really small values, 0.0 to the thousandth, to the thousandths to find that. Okay, if it's 0.1, it's not going to work as well. Okay, and so our graph, let's make that graph. I'll put 1 here, 2 here, 3 here. So 2.71 is around here. I'll go back to my graph, and it was like the graph was coming up here, and then it went closer and closer and closer like that. And so that point is 0, E. Alright, it didn't go through E, but around it, it went through E, even though there's a hole there. Alright, so sometimes we have to use our graphing calculator. I think similar instance with example 6 here. We have approximate the limit. Approximate the limit as the limit of x approaches 0 of the sine of x over x. Okay, this guy. Can we do anything to cancel anything? Because when I plug in 0, I'm going to get sine of 0 over 0. Right? That's going to be 0 over 0. So that doesn't work. So, ooh, can I cancel the x's like this and this? Absolutely not. Those are two different types of x's, right? You have to take the sine of x divided by x. So you can't do that. So again, we just have to put it in our calculator and see what we get. You know, look at the x's, look at the y's in our calculator and see what we get, which is easy enough. So sine of x over x. Sine of x, end your parentheses, divided by x. And you have to be in the right mode or this is not going to work. Because we have a sine, what mode do we have to be in? Radians. Okay, so make sure you're in radian mode. If you're in degree mode, switch it over. Mode, right here. Mode. And then graph. Okay. And it's supposed to be more of a curve. So let me zoom in a little bit. Let me get rid of these negatives. I don't need that negative. And it looks like it's only going to 1. So let's fix our window to +1 and 0 for my x's. Let's change that x to like at least -5 and +5 to get a wider view there. And then I graph. Okay, so I get more of a curve. Actually, I do want to go into the negatives a little bit because this goes past the negative, so let me change that to the minimum to -2, let's say, and then graph it. Okay, that's a little better. So it shows you that you kind of get that Gaussian curve and it dips under the x-axis there. And what are we looking for? The value at 0. It looks like it's at 1, right? So let's look at our graph. Yeah, it goes up to 1 and down to 1. So our value is going to be 1. Okay, if we make it really small, your book says to, wow, we want this actually to go to 0.9. So my table set, I should do like 0.00000001. Let's see if that works. And then do our table. Oh, and I'll have to go. Oops. My table set, what did I do? Let me just do 0. Oh wow, it made it go really small. Let's see. Oh, it still wouldn't do it, so I couldn't get it to go 0.9. But it's approaching 1 each time. Okay, and you can see from the graph that it is going to go up to 1, but there is going to be a hole up there, so because all these values are 1, right, except when we get to 0, it's an error, undefined, And then we get 1 again, 1 again, 1 again. Really, it goes like this. The axis goes through there. And at 0, there is a hole up there, so I shouldn't have put the line. I should have put an empty hole right there. And our limit is just going to be 1, though, because of the graph. So you can get, you know, this isn't oscillating. It's not bouncing up and down like yesterday. We got an oscillating graph. This is just a smooth curve, so there is a limit there. Okay, and lastly, we need to talk about one-sided limits. Okay, one-sided limits. And what was that? You have to check the limits from both sides. Yeah. We just use one-sided limits to check the limit. Okay, so sometimes we talk about, we split the limits up into two things, left side and right side. The way that we write that is this: the limit as x approaches whatever number from the left. From the left, we put a little minus. So that minus does not mean negative, although you can think of it, the negatives are on the left, right? Of f of x equals L. So this is the left-sided limit, right? This means left side. If I want to talk about the right-sided limit, I do the opposite. I put the limit as x approaches c from the right. So I put a plus there. So that means that's the right side, the right-handed limit of whatever function we have. F of x is a different number, or it could be the same number, or it could be a different number, right? So we have the left-handed limit and the right-handed limit. Okay, let me show you how we use these. So that does not mean negative, that does not mean positive, it means left, and this means right. So when you see, you could tell, because it's not before the c, right? If it's before the c, then that's just a negative number. Alright, so let's do example 7 to show you how we use left and right-handed limits. Find the limit as x approaches 0 from the left and as x approaches 0 from the right. So find I'm just going to put the limit as x approaches 0 from the left. I put a 0 minus or a 0 negative. That means 0 from the left of the function, and our function is the absolute value of 2x over x. Of the absolute value of 2x over x. Okay. And we also want to find the right-handed limit, the limit as x approaches 0 from the right of the same function, absolute value of 2x over x. Okay, let's see if we plug in 0, right? Let's just plug in 0 to see what we get. 2 times 0, absolute value of that over 0. You're going to get the absolute value of 0 over 0, which is still 0 over 0, which is still indeterminate. So that tells me there's a hole in this graph at 0. So we have to check what's happening to the left of 0, right? The only way to do that, we could make some kind of table, but our graphing calculator will make that table much faster for us. So let's put it in our calculator. How do you do absolute value again, like we did last class period? Math button, right? That wonderful math button. Press it. Go over to numbers, scroll over to numbers, and then there's your ABS, absolute value of 2x, close your parentheses, divided by x. So it looks like that. And let's graph. And I don't know if my window is going to be good for this. Let's see. Okay, I got a line down here, but I should be getting a line up here too. So let me shrink my window a bit, or expand it up there, I should say. So my minimum, let's make it -4 and +4 for my top function there. And maybe change my x window to, I was going to say -10. Yeah, -10 and +10. Okay, just to widen my area. And this is what we got last time when we did absolute value divided by x. And you're always going to get that when you do an absolute value divided by an x. You're going to get two parts of the graph. This is a, what do we call that when the graphs are split up like that into two parts? piecewise function, right? So the limit from the left is approaching what number? What y value is this? -2. So from the left of 0, it's approaching -2, but from the right of 0, it's approaching +2. So it has two different limits when we're talking. That's why we do left and right, right? So this one is approaching -2 from the left. From the right, it's approaching +2. Okay, we can see that when we make our table here. Thank you. Ashley, for you. And you might want to go after, well, it says 9:15, so we should be good. Okay, so right, but at 0, it's approaching -2. At 0, specifically at 0. So I get an error at 0, right? But at -1, it's -2. At -2, it's -2. At -3, it's -2. Right? As we approach 0 from the left, it's approaching -2. I say it's approaching because at -2, let's say this is -2, there's a hole there, and then it goes like that. At +2, there's a hole, and then it's going to the right. So we say it's approaching -2, but it's not equal to -2. Okay? And at 1, it's +2. At 2, it's +2. At 3, it's +2. So you can see the left-handed limits is -2. The limit from the right hand is +2. They're different numbers, right? So the left-handed limit is different from the right-handed limit. Well, if the left limit is different from the right limit, does the limit exist? No, we learned that last time. They have to go to the same number to exist, right? So, oh, we did the graph already. So this limit does not exist. If we would have got the same number, then this limit would be whatever that number is. Okay. So good, we know about left and right-handed limits. And then your book shows you, it tells you, if f is a function and c and l are real numbers, then the limit as x approaches c of f of x is L if and only if both the left and right hand limits exist and are equal to L. So they have to be equal to the same number L to have a limit that exists. Otherwise, the limit does not exist. All right, and we'll do the last one for today is example 8. Although there's 3 more examples, I'm going to let you read those at home, and we might continue it Monday too. So find the limits as x approaches 1 of f of x. So they're going to give us a piecewise function here is equal to 4 minus x when x is less than 1. Excuse me. 4x minus x squared. All right. So of 4x minus x squared when x is greater than 1. And there's no equal to sign, so that tells me there's going to be a hole at 1 because it's never equal to 1. Okay. This means the left or the right part of the graph. X is less than 1, so at 1, I'm just going to do the values less than 1. So this is the left part of the graph, right? X is greater than 1, so that's going to be the right part of the graph. So it's a lot like doing a left-handed limit and a right-handed limit. Okay. If they meet up, then we're going to have a limit. If they don't, if they're split, if they're apart from each other, we're not going to have a limit. So let's graph. Because x is less than 1, so here's 1, 2, 3. X is less than 1 is this way, right? And x is greater than 1 is that way. So left, right. Okay. So let's graph these. Okay. So I want to graph at 1. So you want to plug in 1 into this function, okay? So if I plug in f of 1 to the first function, 4 minus 1, what am I going to get? 3. So it's at the point 1, 3. 1, 1, 2, 3. There's going to be an open circle there. Now I just have to use the slope to determine how far to go up and over. But remember, there's a left and a right hand part of the graph. So I'm going to put like a dotted line to, I know I'm working on the left hand. So this is where x is less than 1. This is where x is greater than 1. Okay. So my slope is what? -1. So normally I'd go down 1 over 1, but that puts me in the wrong part. So I'm going to go up 1 over 1, up 1 over 1 in the reverse direction to get my graph like this. My other graph, let's plug in f of 1 to the other graph, is 4 times 1 minus 1 squared. There's going to be 4 minus 1, which is also equal to 3. Okay, and you know, maybe I put this in my calculator just to see where it's at. I'll put in, since it's a parabola, it's a little bit harder, 4x minus x squared. Okay, graph it. And I care what's happening around 3, right? So 1, 2, 3, and I know 3 is, so let me put, I'll put trace, and I'll enter in 3, and it'll put x equals 3 right there. I'll press enter, and it'll see it's at 3, 3. So I only want to put this part of the graph, the right hand side, from 3, right? I don't need that left part because that's not, oh, I'm sorry, I want 1, huh? I was thinking 3. So this part of the graph. So I'm at 1, 3, so I'm only doing that part of the graph. I'm not doing anything less than 1. Okay. So this graph is going to go up, and then it's going to go down, like that. Well, since we got the same number, essentially, those are our limits, right? From the left, it's approaching 3. From the right, it's approaching 3. So the left limit is 3. The right limit is 3. Is the limit 3? Yeah, because they meet at the same point. So this limit, as x approaches 1, the limit as x approaches 1 of our f of x, which is this piecewise function, is just 3. And so yeah, just plug in the number, you know, plug in that 1 into both of them. Basically, if they're equal, that's going to be your limit. All right, example 9 and 10. I just want you to look at, I guess I can explain it really quickly so we don't have to write it all down. Here we have 3 piecewise functions. When x is between 0 and 1, your value is 8. So between 0 and 1, my y value is 8. It's an open circle here, a closed circle here, because it's less than 0, equal to 1. From 1 to 2, the value is 10. So from 1 to 2, the value is 10. Okay, it's a step function, right? And then for 2 to 3, when x is 2 to 3, our value is 12. So we're going to jump up to 12 here from 2 to 3. Okay, so we are looking at the limit from 2 from the right, because we want to find the limit at 2. Okay. So, and these are shipping costs, and we'll see if it has a limit. So at 2 pounds or whatever. 2 from the left. Well, 2 from the left, the limit is what? 10, right? What about 2 from the right? If I approach 2 from the right. So here's 2, and I'm approaching 2 from the right-hand side. That limit is 12, right? So one limit is 10, one limit is 12, one limit is 10, one limit is 12. Does it have a limit? No. Different numbers, it does not have a limit, okay? So because the one-side limits are not equal, this does not exist. So, easy enough. Please look at the difference quotient. I'm not going to do this one, but your last 4 problems on your homework, do this. We've done lots of difference quotients. You need to read through it, okay? But, and maybe we'll go over it. I'm sure somebody will ask about it on Monday on the homework. So, if you have, your difference quotient is just, so they're telling you f of 3 plus h minus f of 3. So you're just going to plug in 3 plus h into here for the first part. Here you're going to plug in 3. Okay, so I plug in 3 plus h. And I square it, minus 1. And I do 3 squared minus 1. I get all this stuff, I simplify, I get 6h plus h squared over h. Well, if I plug in 0 over here, I get 0 over 0. But if I factor out an h, right, I could factor out an h in there, then the h's will cancel, and I'll get 6 plus h, and then I plug in the 0, and I get a limit of 6. So it's just a matter of, hey, what do you plug in there? The 3 plus h squared. You square that, you get a trinomial. Okay, so please read that, because you have to do that for number 55, 57, 59, and 67 on your homework. Okay? And that is it. That's your second limit assignment.